Hello, thank you for being here and for your interest in our work. I am Federico, and this is joint work with Margarida Carvalho, Andrea Lodi, Ignacio Rios, and Alfredo Torrico. I would like to point out that Ignacio and Alfredo, they're from Chile, and actually this work studies also how to expand capacities in the Chilean school admission system. Let's start with an example. Let's take in consideration the case in which there is a student, Aisha, and she wants to go to school. So perhaps in her district, there are three schools. There is Montessori schools that she ranks first. Then there is Dewey School that she ranks second. And there is Chateaubriand that she ranks third. Notice also that we have the outside option or the empty school to mean that she wants just to remain unassigned rather than being assigned to other schools. Of course, in the district, there is not only Aisha who wants to go to school, but there are also other students. And each school has a capacity. For example, Montessori school has one capacity, Dewey school has one capacity as well, and also Chateaubriand. And there are a certain number of students, in particular in this simple example, we have 4 students, and each one of them ranks the school according to their own preferences. So also Bob likes first Montessori, then John Dewey, and third Chateaubriand, while both Chaka and Devisha, they like first Montessori school, Chateaubriand second, and they would prefer to remain unmatched rather than going to John Dewey, perhaps because John Dewey is too far from their home. So a natural question, of course, also on the other side, also schools rank students. So for example, Montessori schools like Aisha, then Bob, then Chaka and Devisha. So notice that in this case, we are assuming that all the schools, they have the same ranking. So there is a unique single tiebreaker or master list, as it is known in the literature. So we may match students to schools in many possible ways. In particular, as it is well known, there is algorithm that is called the fair acceptance algorithm that was formalized by Gale and Shapley in 1962 that finds matching that is the best for every single student, that is also called student optimal stable matching, that matches Aisha to Montessori school, Bob to Dewey school, and Chaka to Chateaubriand. Of course, we have a problem here because Devisha is not assigned to any school, which is a relevant problem, of course, because if we are thinking about elementary school kids, then it's definitely a big cost for society of having kids not attending school. So how should we address this problem? This is the topic of this talk. In terms of motivation, centralized matching mechanisms are ubiquitous. We can find them all over the world. For example, as we just provided, the application in the school choice system or college admission system, but also centralized matching markets are seen in job markets or vaccine distribution recently, especially after the pandemic of COVID-19. And recently, there are also some very interesting works on refugee resettlement. One very interesting property of all these matches is stability, which guarantees that there is both a certain degree of fairness in respecting justified envy and also non-wastefulness. Another basic assumption is that the capacities of the schools, for example, or of the hospitals, or of the refugee camps, or the institutions hiring, or the firms hiring employees, or vaccine centers, they are fixed. Is this actually the case in the real world? Well, obviously not. Let's take a simple example. Let's take the case of the province of Quebec in Canada. that is prospecting that in the next couple of years, many tens of thousands of students exceeding the capacities of the college admission system will be applying to higher education. So the centralized government of Quebec is exploring avenues to address this problem. For example, should they build new schools, or should they rent buildings in order to put their classes, and of course hiring new teachers? So the question is, if there is an extra budget that should be allocated to expand or ameliorate the education system, how should this budget be allocated? Especially, we like to think about this question by translating the budget into extra capacities. For example, scholarships or extra positions in classes or schools. Let's go back to our toy example that we saw at the beginning of the talk. So we have on the left the schools, on the right the students. What happens if we allocate one extra capacity to Montessori school and we run the defer, and then we run the defer acceptance algorithm? What we observe is that Bob, who was previously assigned in the case of no extra capacities to Dewey school, improves his own matching and gets assigned to Montessori school. Instead, if we allocate one extra capacity to Dewey school, nothing changes, meaning that no student enters the matching, and no student who was already assigned to the matching improves his or her or their matching. Finally, if we allocate one extra capacity to Chateaubriand school, then we have that Devisha, who was previously unassigned, finally manages to enter the school admission system. So this is, of course, a very good news. So the main question that we want to address in our work is the following. How should we allocate extra capacities? And there are some desiderata that we want to meet. First, we want to ensure a minimum degree of fairness, as we mentioned earlier, in the sense that we want to have a stable matching. We also want to be able to leverage, if we want to allocate extra capacities to prioritize access. For example, in some countries, not all kids have access to even elementary education. And so, for example, centralized governments or private foundations are working in addressing this important issue. Or, for example, we want to allocate extra capacities in the form of scholarships for merit. So to ameliorate the matching of the students who would be already matched into the system. And of course, since usually this kind of decision have to be taken in a very short time window, we want our algorithm to run fast. So let's see our contribution. What is it about? We provide a model formulation that generalizes the model of matching market, because we also embed it with capacity decisions. So not only we decide about the matching, we as the policymaker, we decide about the matching, but we also decide about the capacities. Then we provide several model mathematical programming formulation adaptations. And indeed, we provide a new cutting plane algorithm with a competitive and a very efficient separation algorithm. And we showcase our results both on the Chilean dataset, as mentioned earlier, but also on synthetic dataset, over which we provide some experiments to compare the different mathematical programming formulation to the setting. Finally, we observe that indeed our model manages to empower policymakers by highlighting that there is a trade-off between access and improvement. Concerning related literature review, there are been already given some papers and some works in capacity expansion in the stable matching market. Especially, I would like to mention here the paper by Nguyen and Vohara from 2014, where they study how to ensure that there is a stable matching when there are couples in the market. So stable, how to guarantee that there is existence. And indeed, they provide an upper bound on the number of extra capacities to guarantee existence of a stable matching with complementarities. Then, independently from our work and in parallel to our work, a couple of interesting papers by Kumaran Curino and Duran van der Linden approach the problem of capacity expansion not from a parametric perspective, but from a decision-making perspective, as we do in our paper. But they mainly focus on incentive analysis. So concerning the mathematical programming perspective, which is one of our strongest contribution in this paper, we would like to point out that the first formulations of the stable marriage problem, mathematical programming formulation for the stable marriage problem, were given by Gusfield and Irving in 1989, and then Van de Watt in 1989, and then in the early 90s, there were also Rothblum and Roth and many other formulations that extended also the one-to-one to the many-to-one matching markets with stability. In particular, we are inspired by the formulation of Bobbio and Malinsky from 2000. And we also take in consideration the formulations of Delorme et al. From 2019 and Agoston et al. From 2021. Let's see how it is the model of a stable matching market when not only we decide the matching, but also the capacity decisions. So, as mentioned, the input is given by a set of schools where each school has a certain preference list that we assume to be strict and some initial capacities. There are also the students where every student has a certain preference list or ranking. And then there is the policymaker. And the policymaker has a certain budget of extra capacities that it can allocate to the schools, and there is a penalty. And this penalty captures the cost of having student S unassigned, or the way we represent it, having student S unassigned to the empty school or the dummy school. The output of our model and our mechanism is that we have a capacity allocation and we have a stable matching. So the decision that we can take are first, and this is standard, a matching decision, meaning how to allocate students into the schools. And then we also have a capacity decision. How should we allocate the extra seats to the schools? The constraints we have, the matching constraints, meaning that every student can be matched at most to one school, and every school can be matched up to its capacities. And we have a budget, of course, that meaning that we cannot allocate more extra capacities than the budget, and the stability constraints. And finally, our objective is to minimize the ranking, the sum of the ranking of the students in the schools, plus the penalties of the students that are unassigned. So our problem takes the following form. We have a minimization over the two decision variable of the allocation of extra capacities and the matching of the students. And the sum is the ranking of the students matched to the school, subject to the capacities being allocated up to the budget, and X being a stable matching. So the first interesting observation is, hey, aren't we making this problem too much difficult, while actually it is an easy problem we all often observe that in the real world, the preferences of the students are strongly correlated. So why shouldn't we just allocate the extra capacities to the most popular school? Well, actually, we show that this often does not yield an optimal allocation of extra capacities. Alternatively, so what we do is that we could allocate the extra capacities to minimize the individual welfare of every student, as it is done in the student optimal stable matching that finds the stable matching that is the best for every single student. So what we observe is that indeed under stability condition, minimizing the average rank is equivalent to minimizing each individual rank, which is something that can also be observed by looking at the lattice of the stable matchings. So we have a good news, which is a solution always exists, and we have a bad news, which finding the optimal solution is an intractable problem. We proved this in a theoretical companion paper. So let's see how this impacts the Chilean school admission system. We focus on the dataset of 2018 in the southernmost beautiful region of Magallanes. And there are around 1,400 students. Every student has a preference list of around 3, 4, or 5 schools, and there are 43 schools. So also we embed the data set with an artificial budget that goes from 0 to 30 and 2 different kind of penalties. A relatively low penalty, meaning the length of the preference list of the student plus 1, and a relatively high penalty, the number of the schools plus 1. So what happens if we allocate extra capacities with a relatively high penalty? We observe that on the x-axis, we have the amount of the budget. On the y-axis, we have the number of students who change their assignment as a consequence of the optimal allocation of extra capacities. The green line is the number of students who overall change the matching in comparison to the standard stable matching with no extra capacities. The blue line is the number of students who enter as a consequence of the allocation of extra capacities. And the red line is the number of students who improve the matching, meaning that they were already matched in the system, but now improve their assignment. So what we observe experimentally is that if we have a high penalty, then the model will tend to allocate extra capacities to prioritize access of students who were previously unassigned. On the other side, we have that if we have a relatively low penalty, then the mechanism will tend to allocate extra capacities to improve the matching of the students who are already assigned into the matching. So the first case can be framed into this the case of elementary school kids, and the second case can be framed in the case of, for example, residency program or merit scholarships. But can we also say something about the structure of the problem? Indeed, yes. In the first case, we prove that if the penalty is sufficiently low, then the number of students who enter the matching is greater than the number of students. Well, actually, we find the maximum cardinality stable matching. On the other side, if the penalty is relatively low, then the number of students who enter the matching is smaller than the number of students who improve in their assignment. So again, high penalty, we prove that we find the maximum cardinality stable matching. Low penalty, we prioritize the assignment of students who improve rather than of those who enter the matching. Let's look at our methodology, which is based on the work of Bobbio and Balinsky, which already comprises an exponential number of constraints. We provide, in particular, in order to make it efficient, a cutting plane algorithm based on a competitive an efficient separation algorithm. So as I just mentioned, there are an exponential number of constraints already in the standard formulation of the Bobbio-Balinsky stable matching model. And what we obtain is that we have a doubly exponential formulation when we generalize it to the capacity expansion stable matching problem. We prove that this formulation is valid. But we also managed to provide a couple of structural results. The first is that we only need to focus looking for violated constraints among the schools that are fully subscribed. And second, that we can separate the most violated stability constraints in linear time in the input of the problem. Notice, of course, that the Q star is actually maybe dependent on the number of schools. So actually, in general, this is better than the one given by Bayombarisky, but there may be cases in which they are comparable. Limit cases in which they are comparable, of course. So the cutting plane algorithm takes the following form. We formulate the problem without the stability constraints. We separate, we find the solution and we separate it, meaning that we find the most violated stability constraints, and we add it to the model, and we iteratively solve this problem until we find that no stability constraints are violated. And indeed, we converge because the formulation is finite. So we also have an experimental setup with 1,000 students and 20 schools and a budget that varies from 1 to 30. And we generate for each combination of parameter 100 random instances. So we compare the generalization of the Van de Watte formulation, the linearization of this formulation, and the generalization of the Agoston and Delorme formulation to this setting. So what we observe is that on the x-axis, we have the number of solved instances, and on the y-axis, we have the number of extra capacities, 1, 0, 0, 1, 5, 10, 20, 30. And what we observe is that the only Q formulation that managed to solve all the instances within 1 hour time limit are our cutting plane method and the Agoston generalization through the capacity expansion setting. Indeed, if we focus on these two formulations, we observe that our cutting plane algorithm in red, on the x-axis now we have the extra capacities, and on the y-axis we have the average time in seconds. Our cutting plane method consistently outperforms the Agoston generalized formulation to the capacity expansion algorithm. So indeed, in our paper, we address the problem of capacity allocation. And we address it and we managed to solve it by having stability constraints, providing a trade-off between access and improvement, and having a fast algorithm, which is our cutting plane method. So indeed, our contribution, in our contribution, we have a new model. We provide a new solution approach. We provide the experimental results, and indeed, we also empower the policymakers by providing them with a tool that allows them to decide whether they want to improve access or improvement. Thank you very much for your kind attention.